back and forth. Perfect. Yes. Claire and I have been back and forth, kind of planning this out with the help of Mitch as best as possible. And so we think we've down, but we'll let with each other, right? In our sharing process. So we are presenting from the Prince Lab and the Hutzler Lab. So the Prince Lab will go first, you can see on the agenda, and then we'll have some time for Q&A after. We've allocated about 30 minutes or so for a presentation, 30 to 40 minutes, and then a 10-minute Q&A from the Prince Lab. Hutzler Lab will go after that feedback. We have about a 25 to 30-minute presentation with Q&A after. And then we'll close it all up with some closing remarks. Does that sound good? Any questions? Any logistic questions anyone need before we jump in here? All right, perfect. So I am going to, actually, I'm going to just stop sharing, and Clara, your crew can grab the reins. Let's see, can I stop sharing? What's happening? You should be able to start sharing now if I don't get to this fast enough.
Okay. Well, hello everyone. My name is Clara Garay. I work with Tom Prince's group and Kevin Burgess and the rest of the kids. So it was great. We learned a lot about asteroids. And so I'd like to introduce Tom Prince. He was our faculty, and he will introduce himself and the rest of the group.
Yeah, so hi, I'm Tom Prince. I'm faculty at Caltech. I'm a professor of physics, but most people think I'm an astronomer. Do a lot of work with telescopes at the Palomar Observatory, just south of us, or most of us here. First of all, I want to thank Mitch and Clara for all their work on setting this up. Thank you very much for giving us the opportunity for our group to do its job. And I want to very much thank Kevin Burge, who was the principal mentor of the students. Yeah, there are some hand claps there. As the group knows, I was involved with working on or actually leading a study for the National Science Foundation this summer, so I was very occupied. We had a challenge this year because in other years we've met face-to-face with people, right? With students. And so that's a completely different dynamic than trying to do it remotely. So that's why I chose asteroids and solar objects in our own solar system as the topic, because I thought it would be much more accessible for remote interactions. And I hope that worked. I think the students, I hope they had a good time, and certainly they've done very impressive work learning about asteroids. And so I'm going to stop speaking, and Kevin, do you want to introduce the students?
Yeah, well, first let me maybe introduce a little bit about the overall project. So I'm Kevin Burge, and I'm a graduate student who works with Tom. I was also learning about asteroids for the first time this summer. This is a completely new topic to me, so I had a lot of fun and actually learned a lot from the students. So let me maybe go over a little bit of what you're going to be hearing about over the next 40 or 50 minutes. So there are 4 major categories of near-Earth asteroids, and each student followed up an asteroid that was actually discovered with a telescope at Palomar that we work on, called the Zwicky Transient Facility, from each of these categories of asteroids. And so I learned a lot from them because they actually all did in-depth research on each of these categories of asteroids, and that's what they're each going to be presenting today. Okay, and so our students are Brianna, Finnegan, Sylvia, and Oliver. For me, they're all in the same row on the images. And so you're going to learn a lot from them today. I certainly learned lots of new things. And even Tom, I think, said last time during the presentations that he learned some new things. And he's been working on this topic for quite a long time.
Oh, definitely. Yep.
Yeah. So I can't remember who's going to go first.
It was Finnegan.
It's me. Hi, Finnegan. I go to Poly in Pasadena. Quickly answering some questions. I applied to this program because astronomy is something I really have enjoyed. It's literally the moon calendars on my back wall right now. And I was kind of curious to explore it in a more depth way and see if my curiosity held, and it really did. And I'm glad to be able to share that kind of result with you guys today. One thing I really learned during this program is my logical sense could get a lot better. I'll like read something and say something and not realize, oh, that makes no sense at all. But luckily I had a lot of people with me during this journey to kind of correct me and help me figure that out. And I feel like I've made more sense of that kind of side of myself than I knew at the beginning. All right, so I will talk to you guys a bit about asteroids. If I can find my slides really quick. Hold on. They're up, they're just on the wrong slide and not in present mode. Okay, so I kind of want to start, not the right screen to be sharing. Here we go. I want to start with this headline. I'll give you 5 seconds to read it. That's the asteroid 2019 OK. Full preface, this is not the asteroid type I'm talking about. It's not an A10 asteroid, but it's important because this asteroid snuck up on us. We really had no idea it was coming until about a day or two before it passed us, and it got really, really, really close. And if it had hit the Earth, it would have basically taken out a city-sized area. It's always important to remember with asteroids, oh, I messed up. Point is, it gets pretty close to the Earth. It's always important to remember with asteroids that they can get really close and potentially even impact the Earth and do serious damage. So they're not just silly balls of rock in space. So I'm going to talk about A10 asteroids today. A10 asteroids are a type of asteroid, as seen by this asteroid here, 2018 CL, which spend most of their time within Earth's orbit, but kind of come out for a little bit, which is what's going on, I believe, over here. You may be saying, isn't this bit also coming out of Earth's orbit? Earth is this light blue line here. Probably not, because this asteroid orbit is inclined relative to Earth's orbit, so it's kind of underneath Earth's orbit, if that makes sense. 2018 CL is a pretty average A10 asteroid, as it turns out. I'll talk more about that later, but it's still interesting. It was discovered in February 2018 by the Zwicky Transient Facility at Palomar Observatory. And thank you, Kevin, for helping me track down this image of what it actually looked like when they saw it on the scope when they took a photo of it. It's a very zoomed in photo of it streaking across the sky. The reason I bring this asteroid up is because although it seems like an average asteroid, it hides something very interesting. Like 2019 OK, which I just showed, it's a potentially hazardous asteroid. It could impact the Earth and cause a lot of damage. This is a general theme with A10s. They're not all potentially hazardous asteroids, but they're all kind of doing something interesting and unexpected. So quickly, I should mention, 2018 CL is an A10 asteroid, and that's what I'm talking about today. 2019 OK is an Apollo asteroid. I should clarify. Apollos tend to hop into Earth's orbit just a little bit, while mostly being outside of it, while A10s go out of Earth's orbit a bit, while mostly being inside of it. All right, I also want to quickly talk about the history of A10 asteroids. A10 asteroids were discovered also at Palomar. The first A10 asteroid was discovered by this woman over here, whose name is Eleanor F. Helen. She named this asteroid 2065 A10, and then the word A10 was used to describe the rest of this category of asteroid that had been found. So what is A10? What does that come from? Well, A10 actually means disk, and it was like part of the sun god Ra in Egyptian mythology. Now, to make that more interesting, this guy down here, this pharaoh named Akhenaten, he actually decided that when he became pharaoh that A10 would be the only god. And it was, and this was actually kind of the first monotheistic religion in history. And then quickly after he died, his son changed it back, and everybody forgot that A10 was this monotheistic god for a long time. Guess who that son was? It was King Tut. Point being, A10s again have even a weird and interesting history. They're not as boring as they may seem to be. All right, so what did I do with this project beyond just research? Well, I did a lot of Google Sheets work. Right here is one kind of important orbital mechanical piece of information about asteroids, their apsis, which basically says how far away do they get from an object they're orbiting, in this case the sun, and how close do they get. Periapsis is the close number, it's this lowercase q, and apoapsis is the further away number. So I basically took all A10 asteroids I could find and analyzed the data and saw kind of where generally did their apoapsis and their periapsis fall. I'll put up a different graph, which I actually kind of like better for them. So as you can see, mostly their periapsis and their apoapsis fall in this range here. Their periapsis in here and their apoapsis in here. Now, what's this 1.0 and the 0.50 and all that? That's what's called the astronomical unit, which is the average distance from the Earth to the sun. So since they're Atens, this actually makes sense. When they're closest to the sun, they're closer in than Earth. And when they're further away from the sun, when they're furthest away from the sun, they're further than Earth ever gets. That makes sense based on their definition I shared earlier. I want to do a few more of these. This is called the argument of periapsis. This is the one orbital mechanical thing I really don't understand, but it has to do with the periapsis and it relates to this angle right here. It's important for other things. And as you can see, this is kind of where the data conglomerates, and that's a big spread of data here. But mostly, this is how to read this chart. The maximum is here. This is the maximum argument of periapsis. The minimum is down here, and most of it fits in here. That's where most of the data, they're between 100 and 300 degrees in their argument of periapsis. I want to do a few more of these really quickly. This one I love, inclination. I'll go back a couple slides. Inclination is this angle right here. It basically says how weirdly shaped is the, or how weirdly angled is the orbit when compared to the orbit of planets. And mostly, not too weirdly, mostly it's not too far off the orbit of the planets. But I love this number right here, which is there's an asteroid that's like 60 degrees, like something like this, off the orbit of where planets are, off the orbital plane. I think that's very cool. Last couple I'm going to do really, really quick. This is eccentricity. Eccentricity is kind of how spherical, or not how spherical, how circular an orbit is versus how like ovular an orbit is. Earth's eccentricity is like 0.01, I think, which is very close to 0. 0.0 means a perfect circle, and 1.0 actually doesn't even mean a circle or an oval at all. It basically means a parabola. So not even something that's orbiting, it's just going in and coming about and then never going back. So where do Aten asteroids kind of conglomerate on eccentricity? Mostly somewhere in here. I'll pull that up like this. Mostly they're between like 0.23 and like 0.48 is my guess. That's probably not quite right, but most of their data is conglomerated with in here. But important to note, there are Aten asteroids that get pretty darn close to like being parabolas. You can see there are some that are up here in this like 88 to 90 range in terms of where the asteroids are eccentric wise. So there's some really eccentric ovular elliptical orbits. Well, last one I'm going to do is absolute magnitude. Magnitude basically says how bright something is, but it's a really weird numerical system. I think we actually spent a whole day in this lab talking about how magnitude works. Here's why it's weird. The higher the number is, the less bright the thing is. And if it's negative, a high negative number means it's super bright. So basically you want more negative numbers, closer to negative numbers, being brighter. Asteroids tend to be pretty not bright because they're only light that they're emitting is light they're reflecting from the sun. And so as you can see here, they're up in the 20s range, which is very high, or very low, I guess you would say high absolute magnitude, which means low brightness. They're up above 20 mostly, and they don't even fall that far beyond that. But some are really, really, really dim. Again, there's some weird Aten asteroids. So I did all this research, and I had a lot of fun coming up with all these pieces of information about Aten asteroids. And then I read this paper, and it's about how do we measure the rotational period of an Aten asteroid. That basically says, how do we measure the time it's doing this? How do we measure how long it takes for it to kind of spin and rotate on its axis? This is not a great image, but I wanted to have some image here. This is the asteroid 1992 FE. It's another Aten asteroid. And again, it's actually potentially hazardous. It's another asteroid that could potentially cause damage to the Earth. Important to note, it's not just a normal asteroid. And the reason this paper blew my mind was for a couple of reasons. One, the way we measure the rotational period is we plot on a light curve the brightness of the asteroid over time. That's basically all light curve says. It's how bright is something over time. And as you look, it has kind of this wavy sinusoidal periodic nature. And you can basically take one point and match it to another point that's in the next period. And that's, I think, pretty close to the period of the asteroid. That's what this paper said. In addition to that, this paper then used what's called variable star software, which kind of does this in a more advanced way and is used for dealing with stars that have their light changing over time to confirm how long the rotational period of an asteroid is. And in this case, this asteroid is a bit more than 6 hours. The reason this blew my mind is if we go back a couple slides, I was reporting about the absolute magnitude, how bright something actually is. And And then we go here and it's like, actually their brightness changes over time. So forget all this like absolute science you've come up with and all your data. And then it gets worse because I found this paper, which talks about this asteroid here, 2020 HA10 and 2020 OV1, both of which, if you look at this data, vary on basically all the other counts I talked about. Their apoapsis changes over time, their eccentricity is changing over time, their inclination is changing over time, and their argument of perihelion, or their argument of periapsis, is changing over time. So that means all my data about this concrete knowledge is maybe true in the sense that maybe on average, that's their kind of values for those things. But overall, these concrete numbers I came up with don't really mean anything. And to make matters more interesting, these two asteroids, well, they don't look like A10 asteroids, right? Because they don't seem to go outside of Earth's orbit, except that over time, they do. Because the thing about these asteroids is, I believe because their numbers, their kind of values are actually changing, this paper pointed out that since their eccentricity, inclination, and all that is changing, the actual orbits of the asteroids are changing enough to change their type of asteroid. So this asteroid here, 2020 HA10, is what's called an Atira asteroid right now, but for most of its time, it's been an A10 asteroid. And this asteroid over here, 2020 OV1, does similar things. It's a Atira right now, but it actually was an A10 asteroid. Again, these are what I would call surprise A10 asteroids. They're not, we don't think they're A10s, but then it turns out they are. They're more interesting than we thought. I want to do one more quick study, and then I'm done, I promise. This is called 2014 OL339. This is an A10 asteroid, as you can tell. And the thing that's interesting about 2014 OL339 is it's not gravitationally bound to the Earth, which means, but it is orbiting the Earth, sort of. It's what's called a quasi-satellite. And the paper pointed to this graph that they'd created, which shows essentially this asteroid does this very strange orbit over time around Earth's orbit, which I thought was fascinating because it's like, we have this type of asteroid that I always assume is just going around the sun, but again, it's actually going around, it's interacting with other gravitational bodies in the solar system as well. So I found that to be really incredibly interesting. One more quick fact about it, it won't always be doing this thing. It actually will, in I think another 165 years, become a different type of co-orbital called a Trojan, likely. But it's not going to stay in this kind of weird orbital shape it is right now. All right, so to wrap up, I want to say thank you to Caltech for letting me research orbital mechanics and also ancient Egyptian religions, and most importantly, for letting me look into asteroids. This has been a really fun and fascinating project, and I've really enjoyed myself. Thank you for listening to me too.
Thank you, Finnegan. I believe Brianna will be adding on to Finnegan's presentation.
Hi, my name is Brianna. I go to Pasadena High School, and I applied to this program because I really love astronomy and I wanted to kind of have experience, you know, looking at what all these people research. And I think my main takeaway from this whole experience is not to be afraid of information you don't know. So not being afraid of jumping into a paper and reading it once and you have absolutely no idea what it means, not to shy away from it, but take your time and really learn what it means and be kind to yourself when you don't get it, because you eventually will. So I have a presentation on, oh, let me actually bring it up real quick. Here it is. Okay. I have a presentation on another kind of asteroid. So my presentation is on Atira asteroids that Finnegan actually mentioned a little bit. So what's an Atira asteroid? An Atira asteroid is an asteroid that orbits completely within Earth's orbit. So its perihelion is less, or its aphelion is less than Earth's perihelion. So the point where the asteroid is furthest from the sun is less than the point where the Earth is closest to the sun. And you can see in this little diagram here, this is where the Atira's orbit. And actually, there's one very special Atira called a Vatira. It's a kind of a subclass that are all within Venus's orbit, and there's only one that's been found so far, which is very interesting and very exciting. So Atira asteroids, we only know of, as of now, around 23 of them because of how difficult they are to find. And they're very difficult to find because of how close they are to the sun, because they're within that Earth's orbit. So they're right by the sun. We have to look at the sun to try to find them. So there's only this kind of 30-minute period during twilight that you can actually see these asteroids. So the ZTF Twilight Survey was a survey that was conducted by Palomar with ZTF. And basically they would take 10 survey fields with small solar elongation. And basically solar elongation is the angle of the Earth relative to the sun, and then that's relative to the person observing. So we want a really small solar elongation, and the air mass has to be 0.29, and the air mass has to be less than 0.29. And that air mass just relates to how clear your view is going to be. And once they found those fields, they would take 4 pictures, each of them 5 minutes apart. So then they were able to see the objects moving. Then that data would be processed by Z-Streak, which looked at fast-moving objects, and Z-Mode, which looked at slow-moving objects. And a total of 6 were found during this survey. And here in this chart, we can see that the coverage of the ZTF survey, and these X's represent some of the Atiras that they found. So some trends with Atira asteroids is that they have relatively short periods. The smallest period of all asteroids is actually 151 days. And 2019 LF6 is an Atira, and it has that period. But also the 2020 AV2 Vatira, the one that's completely within Venus's orbit, it also has that period. And the highest period of Atiras was about 271 days. Now, when looking at a chart of all the Atiras, you tend to notice that their diameter doesn't exceed 2 kilometers, but there's one that does, and it's 163693 Atira. And this Atira is really special because it's actually a binary asteroid. So it's one 4.8 kilometer wide asteroid that's orbited by a smaller 1 kilometer asteroid. So it's kind of like the moon and the Earth, except it's an asteroid and then a tinier asteroid. And the inclinations range from about 2, which 1998 DK36 was actually the first Atira ever discovered, and then 49.66, which is a pretty big inclination. And here are some histograms of the eccentricity of Atiras. So you can tell that they don't really, oh, whoopsies. They get to about the halfway point with the eccentricity, but not really. They don't have very eccentric orbits, because if their orbits were super eccentric, then they might go out of Earth's orbit. And also the inclinations, there's a huge range, and they can go from really small inclinations to really huge inclinations. So it's hypothesized that Atiras originated in the main belt, and what the main belt is the asteroid belt, so it's in between Mars and Jupiter. And they believe that these Atira asteroids started out there, but due to different interactions like perturbations, which are basically interactions with planets can change the orbit of the asteroid, and something like the Yarkovsky effect, which the Yarkovsky effect is the sun is emitting photons, and the photons are reaching the asteroids, and the asteroids will absorb or reflect the photons, and the ones that they absorb, they emit as heat. And once the asteroids emit those photons as heat, it creates momentum, and it can either bring the orbit of the asteroid further into the sun or further out from the sun. And it's a really small effect, but it happens over, billions of years, and that's what can kind of change the orbit. Also, if you see the orbit of 2019 AQ3, it looks like it kind of goes pretty, I'll use the pointer here. It kind of goes pretty far out from the plane of the solar system. They think that this happened because Atiras would interact with Venus or Mercury, and that would kind of slingshot them out, to these points, and then their orbits would be very inclined and pretty far out from the plane of the solar system. Okay, so this is something called a dynamical map, and basically it's showing the stability of Atira orbits. And it's based on something called a spectral number. And a spectral number is basically, you have a periodogram, which is like a graph that kind of has something that looks like a frequency. And that graph shows the semi-major axes of the asteroid. And semi-major axes is kind of, think of it like the radius of the orbit in a way, or the diameter. And every peak or every semi-major axis value that reaches above a certain threshold, the amount of peaks that do that is the spectral number. So the higher the spectral number, the least stable the orbit, and the lower the spectral number, the more stable the orbit. So in these really dark areas with the lower semi-major axes, we can see that those are much more stable orbits. These are more dynamical maps, and they aren't based on spectral number. They're based on the log of the maximum standard deviation, but the paper I was looking at proved that this was also a good chaos indicator. And we can see with this bottom graph that it's relatively lighter compared to graphs that have lower, we look at back at this one, you know, the lower semi-major axes are completely black, and those are Atiras that would orbit closer to Mercury, but all the known Atiras are more like these graphs, because we don't know any Atiras that go interior to Mercury. So what this tells us is that the orbits of the Atiras that we currently know about are relatively unstable based on these dynamical maps. And the reason that this paper was studying that is because that might tell us whether those asteroids are hazardous to us or not, because they're really close to us and we need to know if they're a threat or not. So these studying these dynamical maps and using chaos indicators will tell us, is this orbit stable or will it change, and things like that. And so this is 2020 OV1. Finnegan actually mentioned it. And the reason that I found this asteroid very interesting is that it actually goes within Venus's orbit for a pretty long time. So it's not a Vatira, but it kind of, you know, it's almost one, I guess. And it doesn't go within Mercury's orbit, but it does go within Venus's for a while. And based on the graph that Finnegan showed earlier, and based on the behaviors of the, you know, argument of perihelion and the semi-major axis, they think that 2020 OV1 actually became an Atira recently. So it's a pretty young Atira. And with 2020 HA10, another one that Finnegan mentioned, they believe it switches between A10 and Atira. And that's all I have today on Atiras, and I want to thank you all for listening to me.
Thank you, Brianna. All right, next is Sylvia.
Hi, everyone. I'm Sylvia. I think quite a few of you have met me before, either through school or our internship. And I'm going to be a senior at PHS next year, and I joined at the SRC program because I love astronomy. I'm part of Pasadena High School's astronomy club. And I actually did the SRC last year in the astronomy department, and I really, really enjoyed it, and I just wanted to do it again. So yeah, let me share my screen. So I did my research on Amor asteroids, which is, okay. So I did my research on Amor asteroids, which is another category of asteroids. And these asteroids, they're categorized by having periapses, which is just the plural of periapsis, that's the closest it gets to the sun, between 1.017 and 1.3 AU. AU is astronomical units, which is the distance between the Earth and the sun. And they have semi-major axes greater than 1 AU. And semi-major axes, just a simple definition, is if you think about an ellipse, an oval, it has like a long diameter and a short diameter. That long diameter in half is the semi-major axes. And what that means is these orbits are entirely outside of Earth's orbit because they never get within Earth's distance to the sun. And a lot of these Amor asteroids, actually, their orbits cross the orbit of Mars, which you'll see on the next slide. And on the right here is an Amor asteroid, Eros, and it's a very special asteroid because it was the first Amor asteroid ever discovered. Hence it has its own name. It was discovered in 1898, and NASA's actually landed a probe on this asteroid before. So this diagram right here just shows where Amor asteroids are found. That green patch you see goes over Mars's orbit quite a bit. That's where Amor asteroids orbit, and they stay entirely outside of Earth's orbit, which is in the dark green. So Amor asteroids have been found to have a pretty large range of compositions, which suggests that they have a variety of origin sources. And this includes extinct cometary nuclei and asteroids from the main asteroid belt, which basically all asteroids, most of them come from these two sources. So there's actually a hypothesis proposed a little while ago that I read on, and it was that most Amur asteroids are extinct cometary nuclei, so basically the core of a comet once it burns out all the ice and dust around it. And it was actually kind of found that this theory is implausible because most meteorites that enter Earth's atmosphere are actually parts of Amur asteroids or Amur asteroids. And for a comet to become a meteor is basically impossible because comets are kind of like just dirty snowballs and they can't really become asteroids or meteors that would enter Earth's atmosphere and burn out like the way we see them. So that leaves the main asteroid belt as the main source of these asteroids. So some of these asteroids might have been ejected from the Kirkwood gaps through gravitational attractions of Jupiter. And what Kirkwood gaps are is that if you see on the right, this is like a histogram of the distribution of semi-major axes of asteroids within the main asteroid belt. You see there's gaps at like 2.5, 2.8, where there's basically no asteroids with this semi-major axes. And that's because of Jupiter's orbital resonances. Jupiter's orbital resonances kind of throw these asteroids out of these areas. And other asteroids might have also been perturbed from the inner main asteroid belt. So just the part of the asteroid belt that's close to Mars by interacting with Mars. And asteroids could have also interacted with both Jupiter and Mars and then become more asteroids. And on a side note, it's thought that Mars's two moons, Phobos and Deimos, might have originally been Amur asteroids that were captured by Mars. So more asteroid trends. Most Amur asteroids don't have a very large inclination relative to the solar system's invariable plane, which is where most of the planets orbit. And on the right is a histogram you can see. Most of them range between like 5 and 10. That's where you see them kind of cluster up. Average inclination of Amur asteroids is 13.08 degrees, which is actually slightly higher than the other two largest categories, Apollo and Aten. The smallest inclination of Amur asteroids I found is 0.1 degrees, which quite a few asteroids actually do have this inclination. And the maximum inclination is 93.7 degrees, which is pretty much perpendicular to the orbits of the other planets. And this asteroid was 2014 PP69, which I'll actually be talking about later. On the right, below the histogram is the orbital path of 2020 NB, which has an inclination of just over 15 degrees. And this is actually a pretty typical inclination for most Amur asteroids. This asteroid was discovered just about a month ago on ZTF in Palomar. Continuing Amur asteroid trends. So on the left, I have two histograms, and they show the distribution of the semi-major axes of both Amur and Apollo asteroids. I wanted some comparison here and the same for eccentricities. So eccentricity is directly related to semi-major axes. Eccentricity is calculated by dividing the distance between the center of an orbit by one of its focal points. So in this case, the sun, we would use, and then by the semi-major axes. So you see for a lot of the Apollo asteroids, which is in red, they peak, their semi-major axes kind of peak near one point, around 1.12, and they decrease the more you get away from 1.12. And that's actually reflected in the histogram below for the eccentricities. So you see for the Apollo orbits, they kind of peak near about 0.56, whereas for Amur asteroids, they don't really peak. They're a little bit more spread out, not quite like evenly, but generally more spread out, so there's less of a peak. And you'll notice in the histogram for the eccentricities that these Apollo orbits, their range extends from 0 all the way far out to 1, whereas the Amur asteroids, for the most part, it goes between somewhere like 1, around 0 to like 0.6, 0.7 at most. And this is pretty much explained by the definition of Apollo asteroids themselves, which are, I think Finn mentioned earlier, they're outside of Earth's orbit for the most part, but they go in a little bit. And to basically cross a mostly circular orbit, you need to have some eccentricity naturally. So that's why the range is pushed so much further. So 2014 PP69 was the asteroid I mentioned earlier, and it's a very interesting asteroid. So its periapsis is 1.25 astronomical units, which would qualify it as an Amur asteroid. However, its apoapsis, the furthest away it gets from the sun, is 41.39 AU, that extends beyond the orbit of Neptune and even quite a bit into the Kuiper belt. And its inclination is 93.65 degrees, which is extremely, extremely high. And this also means that it has a very large period of 98 years. And this asteroid was discovered in 2014. using NASA's WISE telescope. So not by ZTF, but it was still a very interesting asteroid. WISE stands for Wide Field Infrared Survey Explorer. And its orbit, because of its eccentricity, it's most likely an extinct cometary nucleus with a very low albedo. And albedo is basically how reflective an asteroid is, and this helps determine the magnitude. However, because of its low albedo, its likelihood to have such a low albedo, and its magnitude of 20.0, the asteroid would have to be extremely, extremely large, maybe a kilometer, if not more, in diameter. This you can usually determine actually the albedo and thus the size and magnitude by comparing the infrared emissions and the amount of visible light reflected by the asteroid. However, it passed Earth at a distance of 0.43 AU, which is actually pretty far. So we couldn't determine that much about the asteroid, but this meant that it wasn't really a hazardous object. So we don't have to worry about having kilometer wide asteroid crashing into Earth. Yeah, so on the right is basically the orbit. The blue line is Neptune, so you can see its orbit extends pretty far out. And yeah, that's my presentation. Thank you.
Thank you, Sylvia. Okay, I believe Oliver will add on to the rest of the group's presentation.
Hi, my name is Oliver Hoffman. I'm going to be a senior at PHS this year. I joined SRC because I'm fascinated with space and specifically orbital mechanics, which was great for me because I got to learn a whole bunch about that here. I think the main takeaway for me is how people go about actually discovering asteroids, because that was never something I had considered before. So I'll be sharing about Apollo asteroids. Let's see. So Apollo asteroids are defined as near-Earth asteroids with semi-major axes greater than 1 astronomical unit, which means for most of their orbit, they're farther from the sun than Earth, but they do come closer to the sun than Earth over the course of their orbit. And because they cross Earth's orbit, they're considered potentially hazardous. So it's really important for us to keep tabs on these. This orbit right here is actually the orbit of the first Apollo asteroid ever discovered, which I'll be talking about in a moment. Here we have some trends about Apollo asteroids. The main interesting points here for me are the inclinations. As you can see, Apollo asteroids are generally pretty low in inclination, which means they're close to the orbit of Earth and other planets in their degree tilt relative to the solar system, and the eccentricities, which shows how non-circular they are. The higher the number, the less like a circle the orbit is. And Apollo asteroids are by nature fairly eccentric because they have to cross the Earth's orbit. But they kind of sit in the middle range of eccentricity, right around 0.5, similarly to Sylvia's histogram. So the first Apollo asteroid ever discovered is 1862 Apollo. It's really interesting because it actually is a binary asteroid, which, as was mentioned earlier, is an asteroid with a little asteroid moon around it. 1862 Apollo also has protrusions around its equator, which makes it have a really interesting shape. Here you can see 3D renderings based off of the light curves, which is just how bright the asteroid is as it rotates. 1862 Apollo exhibits the Yarkovsky and Yorp effects. We mentioned the Yarkovsky effect a little while ago, and that is what happens when the sun interacts with asteroids, and the photons from the sun either bounce off of the asteroid and impart their very small momentum, or they're absorbed by the asteroid and re-emitted after the asteroid has rotated a little bit. This produces a thrust in the opposite direction, similar to how rockets work. The Yarkovsky effect deals specifically with how the orbit changes as the asteroid pushes itself around in space. And the Yorp effect deals with how the asteroid's spin is altered by this interaction with the sun. Some famous Apollo asteroids that have been in the news recently are Bennu and Ryugu. Both of these have high-profile return missions targeted to them. JAXA's Hayabusa 2 mission is actually on its way home from Ryugu right now and is going to re-enter Earth's atmosphere in early December this year. And OSIRIS-REx from NASA is about to do its first sample collection run on Bennu. Here's the orbits of Bennu and Ryugu. They are not super interesting, but that makes them good targets for missions because they're very close to Earth's orbit. Here is an Apollo asteroid that was discovered really recently by ZTF. It's similar to the orbits of Bennu and Ryugu, and it's not very interesting, like appearance-wise, but it is a pretty standard Apollo asteroid. One really interesting thing that I found out about Apollo asteroids is that they're largely unstable in their orbits because they have to pass through the orbit of the Earth, and many pass by Venus and even Mercury. They're susceptible to being altered in their orbits by these planets. So it was originally theorized that they were being replenished by deactivated comet nuclei, which means as comets have all of their ice taken off of them by the sun, they become asteroids that are in Apollo orbits. But it was determined by Whipple's classical model, which I'll talk about in a minute, that asteroids can't be formed from cometary nuclei. And here we have an image of the Neowise comet that passed by Earth pretty recently. So Whipple's ejection model is a descriptor of how comets shed mass as they move around the sun. The same actually ends up applying to asteroids, but as I'll talk about in a moment, the asteroids aren't as susceptible to this. The ejection model is based on a few parameters about the distance to the sun and information about the particulates. Some Apollo asteroids, because they cross Earth's orbit, they're actually related to meteor showers that are just little pieces of rock that end up in the Earth's atmosphere. It was originally theorized that these pieces of rock come off of the asteroid via interaction with the sun. But as it turns out, asteroids don't shed very much mass when they interact with the sun. And so it's been determined that asteroids likely impacted other objects, and this is what's causing all the debris. Specifically, the asteroid 3200 Python, which is an image here, is correlated with the Geminids meteor shower. We have the orbit of 3200 Python here. Another meteor shower is the Delta Leonid meteor shower, and this one was of special interest to me because it was discovered by the asteroid is 4450 Pan. This was discovered by Palomar back in 1987. ZTF was not around, it wouldn't be for another 20 years or so, but it was discovered at the same location. A really interesting set of meteor showers is the Taurid-Aritid complex. These are they're related meteor showers because they come from the same parent object, which is an Apollo asteroid called 2004 TG10. The asteroids, the debris from this asteroid and a number of other asteroids that I'll mention in a moment actually come and intersects the Earth's orbit at a roughly 120-degree angle from each other, which corresponds with a 4-month difference between the Taurids and the Aritids, which occur in October and June, respectively. So there are actually 7 asteroids, all Apollos, that are suspected to be the source of these meteor showers, which are Hephaestus, Icarus, Jason, Morpheus, 5025 PL, and Olhato, I believe is how that's pronounced, along with, of course, 2004 TG10. And by having this many asteroids feeding the same meteor showers, you can get around the fact that asteroids don't shed very much mass. If you have like 7 or so asteroids, just their natural degradation from interactions with the sun will more than be enough to feed these meteor showers. And that's it for me.
Thank you all. That was well done, guys. All right. Now this is an opportunity for questions and answers from the group. Just very quickly, for any non-Prince lab members or group members, did you guys keep track of the 4 general asteroids that the kids went over? Did anybody? Just for fun?
Yeah, there was the Apollo asteroids, the 18 asteroids, the Amur asteroids, and oh gosh, there's one more, huh? Yeah.
I think the first one I forgot too. The Terra or Apollo. Finnegan's. I think his I forgot. Right.
You both have, you guys have them both between the two of you.
Right.
Them all up.
The 18.
18 was mine.
There was one that the orbits were interior, and they were
Atira.
Atira, that's the one. Yeah, thanks.
Exactly. It was Aten, Atira, Amor, and Apollo. Okay, so questions and answers from anybody.
I actually have 2 questions. One was during Brianna's, she said V tier and E tier, so I wasn't sure if, because my ears are messed up, so I wasn't sure if it was just me or if there's like 2 different.
Yeah, so there's Atiras and there's Vatiras, and a Vatira is a subclass of an Atira, and it's called a Vatira because it's an asteroid interior to Venus's orbit. So it's still interior to Earth's, but it's also interior to Venus's.
And then my second question was, can you guys explain further what a histogram is?
Does anyone else? I can explain it. Okay. So a histogram is basically it's kind of usually there's intervals, and basically it looks similar to a bar graph usually, but a histogram is where each interval you can have a bar, and that bar shows how many times something occurs within this interval. So for mine, say just inclination, you saw the bars going really high around like 5 degrees, 5 to 10, 10 to 15. What that means is that there's a very high frequency of objects that have an inclination between 5 to 10, 10 to 15 degrees.
And jumping it off that, in case this was confusing, I can't remember if anybody else did, but I also used these kind of bar charts, which basically say, if you divide the data into like 4 quarters, like the total number of data, and you take the lowest quarter, which is like kind of outlier data, and the top quarter of data, you mark them with these lines, and then the rest of the data, the quarters one, the other quarter, sorry, I messed it up. 4 quarters of data, you take the first through third quarters and put them in here, and then you kind of take the outlier data points and put them on the edges. And so I just like that because it kind of shows where the data is most concentrated, as opposed to the other kind of histogram graphs, which don't show that as well, in my opinion. Yeah, hope that helps.
Thank you.
I have a general question, just if any of you want to share, what surprised you the most when you started diving into this? What, were you just like, wow, wasn't expecting that, anything like that?
I think what surprised me most was how many different asteroids there are. I didn't think it was that diverse at all. I think that surprised me a lot.
I think for me, actually something that I learned while doing this was basically the vast amount of resources I could access just for free. So Minor Planet Center is actually where all this data is coming from, where I pulled it from. And I was able to access a lot of papers for free, or through Caltech. So yeah, I think just through this internship, I gained a lot of access to resources that I didn't know about before.
I think something that surprised me was how little there is on Atiras, because we only know of like 23 of them. So it made my research harder, but also easier at the same time, because there weren't that many papers, but there also wasn't so much that I had to research. I think that was pretty surprising.
I
have
just
a question. Oh, go ahead.
I was gonna say I have a comment, and then Ethan, I'm gonna shoot it to you. You guys all sound like you already have your PhDs. Number one, I'm super impressed with the use of content lane, the ability to analyze the data, organize it in graphs, interpret it, was like just jaw-dropping. And I wondered, how did you guys collaborate with each other? Was a lot of your research independent? And was there at some point where you were collaborating on the research you were doing?
Our research was mostly independent. I would say we were assigned, basically we had an assignment where we had to write a report on an asteroid we found interesting. And it just so happened that every one of our asteroids was part of a different group. So we all kind of split off and studied our own group of asteroids, but then we all presented to each other and kind of gave each other feedback on what we could add and what we might want to take out, and also any information that we might have that would be useful to the other person in their presentation.
Very impressive.
I'll ask Sylvia, just so you've experienced SRC face-to-face where you were at Caltech every day versus this.
Yes, I missed
Yeah, we all missed being together in real time, but were there any advantages to this that you thought were useful? I mean, this is going to be our future for a while, so.
I think, I guess you could call this an advantage, but last year where I actually spent more time in person, I was writing programs, doing a lot of coding, doing more of the actual analysis of code, and not so much research on, like, say, a certain aspect of what I'm looking at. So this year I was looking at asteroids. I looked a lot more at data just focused on eccentricity, how the eccentricity would correlate with other things like say major axes, whereas last year I wasn't researching asteroids. I was actually researching binary stars, but last year I didn't spend that much time just looking at how each of these, I guess, properties of what I researched were like and how they related to each other. So I guess you could call that an advantage, yeah.
I have a question, if any of y'all can answer. My question is, do you guys know if there's any other type of asteroids other than you guys had researched? Like is it a big spectrum, or is there a couple more? Like maybe 1,000 or 100,000?
So you kind of broke up at the end, but there are a lot of different asteroids. The ones we did were more near-Earth asteroids, so they were close to Earth, but there's asteroids in the main asteroid belt, there's asteroids in the Kuiper belt, there's asteroids by Jupiter, and there's, the Trojan asteroids, and yeah, there are a lot of other asteroid groups, but we just did kind of the ones that were closer to Earth. And anyone else can add to that.
Yeah, I'll jump in with two things. One, I mean, we talked about the four main types, but quote unquote, there's a fifth type, which Brianna talked about as kind of a subtype. The Vatiras, if we find some more, which presumably there are, might be classified as another type of asteroids. The other thing I would say is that when I think about asteroids, or most anything that relates to like planets and the solar system, I always try to think about like imagining other solar systems. And I have a feeling that there are probably totally different asteroid relations in other solar systems that we are unaware of. So that's a whole new world out there too, I'm curious about.
Wow. Okay, Prince.
I had one quick question, unless we are running short on time, and I can save it for later.
Go. Ask.
So I was really interested by this Gurovsky effect, and where the light is kind of changing the trajectory of the asteroid. And initially I thought it should just push it away from the sun, but I was kind of convinced by your argument about it rotating and then re-emitting. And I was just wondering, is it understood kind of how this effect, when does it push the asteroid away or closer, or is it kind of random, or does it depend on the composition of the asteroid? It seems like it would be tough to model.
So, Oliver, do you want to answer, or should I?
You go ahead. I'll add on if I need.
Okay. So because the asteroid is rotating, like you said, the photons, when it emits as black body radiation, are emitted either against the orbit of the, like against the direction the asteroid's going, or with the direction. So if it's with the direction, it'll speed up the orbit, but if it's against it, it'll slow it down. And if the asteroid gets slowed down, it'll go further out. But if it speeds up, it'll go further in. I'm pretty sure. Yeah. I might have mixed that up, but I'm pretty sure that's...
I think if it speeds up, it has more energy, so it would go further out.
Yeah, further out, yeah. So when it slows down, it will go in because of the gravity. Yeah, you're right. And then if it speeds up, it'll go out.
Okay. Any other feedback we want to offer the Prince team? Yeah, you guys are awesome. Congratulations. Sounds like a very fun summer. All right. Are you guys ready? That's our team. I'm going to share my screen again. Again, my name is Tashonda, and I was the teacher partner in this group. This was my second year with this particular lab. Each year, I'm challenged with learning something new myself. Last year, we built lasers, or the students did. And this year, we got to do some coding. So I got to participate and learn with these very brilliant individuals on how to do such a thing, because it was also very new for me. I'm an environmental teacher, so I don't do too much coding in my class, but I will this year because I have learned. So I would like to introduce you to our faculty leader, Nick Hutzler. He's going to talk about his lab.
Hi, can you hear me? Great. So I'm Nick Hutzler. I'm a relatively new professor in the physics department at Caltech. I'm also I was a Caltech undergrad, so it's fun to be back after being away for a while. And in my lab, we use precision measurements in exotic atoms and molecules to search for new fundamental particles. So what I mean by that is, normally when you want to study a new particle or discover a new particle, you go to like a big particle accelerator, these gigantic super high energy colliders, and you try to just make the new particles directly and then detect them. So you may have heard of the Higgs boson. That was the most recent kind of new particle that was detected several years ago. Maybe, I guess, 6 years ago now, I forgot. Something like that, 7 years ago. And that works. But that's not the only way you can look for new fundamental particles and forces. You can also try to see if they interact with regular matter that you can probe very precisely. So we, for example, look very, very closely at things like electrons or nuclei. And we try to see if these new fundamental particles or forces are interacting with them. In particular, we're trying, finding new particles and forces is just maybe intrinsically interesting, but there's a very particular motivation that we're trying to find a very specific type of new particle or force, which is the new particle or force that was responsible for the creation of matter in the universe. So after the Big Bang, there was a lot of energy. From Einstein's theory of relativity, you can turn energy into matter, into mass. But it turns out that according to everything we know, whenever you create matter, you should always get equal amounts of antimatter. But there's no antimatter in the universe, right? Like all the asteroids that the other team was looking at all summer, they were all made out of matter. They weren't antimatter asteroids. There's no antimatter anywhere. You have to work very hard to create it in a laboratory. Even though, as far as we know, the universe should have no preference for one over the other. But it does, and we want to figure out what particle or force created matter preferentially compared to antimatter, and we do that by doing very precise measurements in atoms or molecules using lasers to try to see the influence of these new particles or forces on those molecules. We have to do these measurements have to be very precise, and so we need things like lasers. But we also need cryogenics to cool the molecules to very low temperatures, because we don't want things like heat or random motion to interfere with our measurements. We want to cool them to as low a temperature as possible so that they're basically not moving, so that we can probe them as precisely as we can. So we have these cryogenic refrigerators in our lab, and we have to synchronize all of our measurements to this refrigerator, which it turns out it's like a cyclical refrigerator. It has basically like a little motor in it that has some periodicity. So the temperature of our molecules actually is slightly periodic, but we want to be able to synchronize all of our lasers and all of our measurements and everything to that periodicity. And that leads into the project that the students worked on over the summer, was to actually build circuits to do that. You know, circuits and programmed microcontrollers to do that. And I'll let them take it from there. Well, actually, first I'll introduce Arian, who's on the call, wearing the mask. Arian's a graduate student in the group, and I'll let Arian introduce himself.
Yeah, hi everyone. So I'm in the lab, which is why I'm on my phone. So apologies, my webcam setup is not as professional. Yeah, I'm a fourth-ish year going to be fifth maybe year grad student in Nick's lab. And I just want to show you real quickly. This is this sort of refrigerator that we have, and if you could listen to this, do you hear this sound? Let me know if you hear that. Yes, no?
Yes.
Yes,
It's
that's
quiet,
the sound.
but you can hear it.
Yeah, so I mean, I guess the background rejection is pretty good on these mics now, but that sound is the sound that a refrigerator makes that we wanted the students to synchronize to. So without further ado, the students will sort of get started with their presentation. It was a wonderful working with them. They're Ethan, Isael, and Destiny. And I'll let them take it away from here.
Well, this is the SRC summer internship. We did it for 5 weeks. We were collaborating with Caltech, and this was mainly just to help the Hutzler lab with their project. Next slide. My name is Destiny Patton. I go to Pasadena High School. 3 facts about me is that I want to be a mechanical engineer major. My favorite subject is lunch, and I am a senior.
My name is Isal Damon. I go to Pasadena High School. I'll be a senior this year. 3 facts about me is I want to major in software engineering or mechanical engineering. I'm not sure yet. My favorite subject is computer science. And I joined SRC to kind of help me choose what major I want to.
Hi, my name is Ethan Yanez. I also attend Pasadena High School. 3 facts about me. I want to be a software engineer, and my favorite subject is math and computer science. I joined SRC to expand my horizon in engineering, just like Esau said, figuring out necessarily what I want to do as my major. So this is our table of contents, basically what we're going to be talking about. We have about 8 slides about all the stuff that we had done throughout this internship. Each slide explaining, going into depth about everything that we have done, everything that our goals, the stages, completely everything, the complete aspect, going into detail about why we did it, the reason that it's going to impact Nick and everyone in their lab with the project that they are working on right now.
So about the internship, this summer we participated in a summer internship opportunity to collaborate on a project to help build a prototype to help the Hutzler lab using an Arduino Uno. We spent 5 weeks of our summer learning how to both code and use Arduinos, as well as other components like oscilloscopes, microphones, and LEDs to help create the prototype.
So the scientific impact that this had on the Hutzler lab. So the lab is a research for the particles and forces by measuring cold pulses of molecules. Like Arian said about the refrigerator, how the sound that you hear, we want to get that in sync with Arduino, with the Arduino Uno, which is what the main impact of the project was. The experiment is pulled by a cryogenic refrigerator, which was what he had showed. The temperature of the refrigerator isolates and produces the sound. So we're helping to create a prototype for the Hutzler lab. The purpose is to aid in finding out more information about the universe, which are those particles, are those new particles that we're trying to find out.
So this is the project details and outline. This is how it looks like. The mic, basically sound above the threshold, it'll output a high voltage, and sound below the threshold, it'll output a low voltage. And the precision potentiometer, it's a knob that helps us adjust the delay time before the mic hears anything. And yeah, we could adjust that between 0 and 1 seconds, or even above that. We would just have to change the code. The LED lights up when the mic reads sound. The breadboard is a board for making an experimental model of an electric unit. And the Arduino is a microcontroller that is equipped with digital and analog input-output pins. So in the outline, the yellow wires are all the output wires. The blue ones are the power, and the red ones are ground. And this is how you would connect everything.
So this is the project stages that we went through. This is the entire thing from July 17th to August 14th, which is today. For the first week, we mainly got our materials. We had to go to Caltech and pick them up. We were told to research about the Arduino, get familiar with some of the things that they gave us, such as the jumper wires and the DuPont wires and the mics, like Isael had previously mentioned. The second week, we actually started working more on projects. They told us to do different small projects, and so we worked on those. We'll get more into that later on. We worked with microphones, LEDs. Week 3 through 4, we started getting into more complicated projects that actually related a lot more to the Hutzler lab. And then week 5, we were doing this, like preparing our presentation, and we are like completing the overall internship, and today is our last day. Next year.
So these are our milestones slash goals. So like she said, from the first week, which is the one on the far left, it's our simple LED project. That project consisted of us getting familiar with the Arduino, the breadboard, and some of the input and output wires, getting as simple as just getting an LED to light up, which is just creating a circuit for the LED to light up. So our second milestone that we came across was combining the first milestone and adding more to it, which is using the LED to light up when using a microphone, using sound waves that the microphone converts into volts, and power sends signals to the Arduino, which sends back to the LED, giving us feedback, showing us that there is voltage flowing through, and our sound waves are providing that power to light up the LED. So then we also use those two into the next milestone, which is working with the oscilloscope. The oscilloscope, basically we used to read the voltages that would pick up every time that we mixed into the microphone. The microphone took in sound waves, converted into voltages, and that would send to the Arduino, which also would have the light up. But then from the Arduino, it would also send to the oscilloscope, which we would read with a ground and a voltage pin that showed us our sound waves, which we will demonstrate in the next couple of slides. And then the last is the outputting the pulse with Arduino. This is combining everything. All of this is the last milestone, combining everything that we had used previously, and taking the sound that Arian provided us from the lab that was coming from the cryogenic refrigerator, and using that sound to sync that sound with the oscilloscope that will show us the the chart and like the waves?
Our thought process, well, our mentors and teachers, you know, they had provided us with several references that we could use. And those were mainly YouTube videos and other instructional videos. So some of us followed tutorials from smraza.com. And we also, again, looked online for YouTube instructional videos because there are a ton of tutorials involving Arduinos that you can look on. And that's what a lot of us used for both coding and actually putting together sequences for the projects. And if we still didn't understand something or something was confusing and the videos didn't really help, then we always have meetings 2 times every week. So we would just talk then and ask questions, and our mentor, teacher, and Mr. Nick would help us, and we would all discuss it and talk about everything that's going on and what ways we can fix it, and also discuss our next milestones. So that really helped. We also could easily email or talk to our peers as well, because I know that my peers were like further than me in the project, so I could like reach out to them and ask them questions as well.
Yeah, so this is our demonstration of the project, the final product, I would say, and here's how it looks like.
Tashanda, I don't think you have the audio picking up the video.
Is it not picking up? It's very, it's kind of quiet. Hold on.
I think you have to, yeah, there's a setting where you can share audio in addition to sharing a screen. So you don't need to have your speaker. It's just like Zoom when it shares the screen, you can also share the audio.
Okay, give me 1 sec. Make sure that I've.
Yeah, if it if it doesn't work, it's that same sound that Arian had in the background. Arian made a recording of it and emailed it so that they could, you know, test it safely from home.
There you go. That, because if I find it, I'm probably gonna hang us all up. Let me just play it one more time. And the sound that you're hearing, the refrigerator sound that coincides with the light. Sorry if I didn't have the actual.
I heard it this time.
Heard it? Okay.
Yeah.
Yeah.
So now getting out of it. There we go.
So we all had different problems coming across throughout these couple weeks. For me, my wiring problems, I had trouble getting things to connect to the right pins and figuring out the right circuits to create, so I would receive power and get everything to flowing properly, getting all the stuff to read, the oscilloscope, the LED to be lit up, and then also all the wiring so we could get responses from the Arduino. Some coding problems that came across, some mistakes in code here and there, not being able to have the right inputs or outputs that I had in my code, which is one of the problems, or a little bit confusion, like being confused with say like delay times or figuring out what's the proper delay or like what the time between the like the values that we want to receive. And then the oscilloscope too, which was honestly probably the biggest problem that I had, was figuring out how to get it all set up. There was different knobs, there's different things, the triggers, the channels, to see where the waves would come up. I had a lot of trouble with that, but those were the main problems that I had throughout these couple weeks.
Yeah, I would say we all had similar problems. For me, same thing. Wiring was an issue in the beginning. Wasn't sure what connected where, but after a few videos and a few meetings, we figured out what goes where. Especially for the a microphone in the beginning, we weren't sure what goes where. For coding, I had problems with coding the potentiometer. It was actually a formula used for the math so that you could adjust the values, as well as the oscilloscope. I had problems with the differential probes because most tutorials use different other probes, and so I kind of had to ask Nick how it worked. And after a few meetings, yeah, we figured out how to use the probes.
I'm pretty sure that Isael had mentioned the microphone, and I just wanted to say that for the microphone, Nick had literally said this the very first day, I think. Yeah, the very first day, that the microphone has three connections. There's OUT, I just call it out because I don't know the proper vocab words yet, but there's out, there's VCC, and then there's GNP, which is also ground. And so when you're connecting the wires, you're supposed to connect the 5 volt to the VCC, and I connected it to the out, and so that ended up burning up my mic. And we were literally told the very first day like which wires to do, and I had written that down, but then I was just out of it because I was like doing something else and plugging it in. So that really taught me to like make sure I pay attention. But luckily, our mentors and teachers were really accommodating, and so I was able to get one by like the next few days to continue. But still, I just that was one problem that I went through. But my major problem was time, because I had another program that I was in until August 1st. And so doing both things was like really hard because I, again, didn't really have that much time to do my projects, and I was falling behind. But luckily, they were really accommodating and helped and made sure that I was caught up. And every week they helped me by like telling me what was going on. And if I was confused, because I'm more of a visual learner, and so like Tashonda, she actually really helped me with that because she's also a visual learner. So she like showed me how to do it and gave me like YouTube videos when they show you like exactly which plugs to plug in and where. And so that really helped. And like they were just really great, and it actually helped me catch up in the end. And I feel like that's really important, especially for research projects where you're supposed to be collaborating and everyone's like supposed to be together. If someone's falling behind, it's really important to have a team that will help you and make sure that you're still on board with everything that's going on. Because even though I was behind, I still knew what everyone was doing and what track they were on. And so that's really important. But coding, I was just a whole mess with that. I'm not a very great coder, so that was also a problem. But again, my peers helped me, my mentors helped me. So that was a great solution to that.
All right, awesome. Is that it? Do you guys want to? Good with your?
Yeah. Thank you for listening.
Yes,
thank you.
thank you. We appreciate it.
Oh, I have to say, these kiddos here, these young adults, I'm sorry, were really balancing a very heavy load. They each had other programs they were committed to, and they still plugged in every week and, like Destiny said, helped each other out. And I think that it showed that they were able to reach their goal, but that they also learned a lot about themselves and their work ethic and their abilities. At least I hope that's what I saw along this journey with you guys. And that no matter how difficult it got, that you guys had it and you were able to get it done. So kudos to you guys for reading it. I was always impressed with your work and your abilities, and even more so with your responsibility and accountability for each other in the project. So now we open it up for any feedback or questions.
I have a quick question. First, I want to say I really enjoyed the presentation, and I think it's really great how you all work together and kind of bounced off each other and no man left behind. I thought that was really great. But a question I have is, you guys mentioned a lot of coding. I don't really know how Arduinos work, so would you like write code and then transfer that to an Arduino, and what would you write the code in, and how did that kind of work?
So the Arduino has its own software, and luckily it's like very similar to JavaScript. So we kind of knew JavaScript already, so it was pretty easy learning it in the beginning. But yeah, I think the only difference is in JavaScript you can be like messy, and it won't like matter. But in Arduino it does. Like you have to be really neat, or else it won't work. But yeah.
I have a comment and a question. First of all, the presentation was beautifully put together. The makeup, the aesthetic, I really liked it. It was easy to read, easy to focus on. Not too many words. I really like that. And a question, I don't know if Ariane or someone said it earlier, I just didn't catch it, but the oscilloscope, I know the refrigerator was basically emitting sounds, and there were like basically waves being measured. So what were these waves or sound waves of?
You guys want to go ahead?
Can you actually repeat your question just one
Yeah,
more
I didn't hear
time? Like the
Cozy, yeah.
end part? Yeah.
Yeah.
Oh, sorry. So basically the refrigerator or the oscilloscope was measuring frequencies and emitting sounds. So what were these frequencies or sound waves like being measured of?
So the sounds weren't made by the oscilloscope; they were made by the refrigerator. The refrigerator, once it's, I think it's called oscillating the particles. The refrigerator creates the sound, and we took a sample file, like a sound file from the refrigerator that was taken by Arian, and that was sent to us using a microphone that was hooked up to the Arduino. That microphone took in those sound waves, converted it into volts, and then sent it to the Arduino so it could send it to the oscilloscope. Which the oscilloscope in the video, you could see the sound waves. If I can demonstrate real quick, the sound waves that it was making. Right here, you could see. I'm not sure if you could see if it's big enough. But right here, once he starts playing the sound, you can tell that the waves are coming out. These are the voltages that are coming from the sound waves that are created and are transferred into the oscilloscope, which the oscilloscope takes and shows you basically every time it makes the sound, the wave bounces, which is showing you basically what we took from the refrigerator and converted it into the oscilloscope.
Yeah, to elaborate on that, the frequency of the sound, I believe, was 1.4 hertz of the refrigerator. So yeah, that's kind of what the measurement was.
And maybe to just put it in some bigger context and connect it to some sort of experimental research ideas that are relevant for our lab. It's very common in an experimental laboratory that you have different pieces of equipment that you want to synchronize, right? So you want the laser to shoot, and then you want the detector to start detecting, and then you want the computer to start analyzing the data or something. And so you want these sort of sequence of events to happen. And a standard way that that is accomplished in the lab is that all these instruments just send voltage pulses to each other. So something will, the laser will fire and then output a voltage pulse to the detector. And when the detector receives a voltage pulse, it will say, okay, I'm going to detect now. And then when it's done detecting, it sends out a voltage pulse to the analyzer, and the analyzer says, the detector's detected something, I'm going to analyze it. And so, this is called syncing or triggering. And this refrigerator, so most scientific equipment, it has these things built in, these like input triggers and output triggers, so you can hook them all up and synchronize them. This refrigerator does not, surprisingly, have this, but it emits this sound. And so we thought, well, we can just listen, and we can make some circuits to just output voltage pulses when this thing makes a sound. That way we can take those voltage pulses and send them around to the lab. So in case it wasn't clear, all of what they did was in their homes over the summer. No one was in the lab for obvious reasons over the summer. And so for them, making the LED blink, so they had a voltage pulse just make an LED blink. And so we could take that voltage, eventually in our lab and use it to synchronize all of our equipment. So that's what and the oscilloscope was, for example, it was largely for debugging. It was just so you could see these voltage pulses and make sure they were behaving the way you wanted to. But you had this sound coming from the refrigerator, which already recorded, sent an, emailed it out. The microphone turned that sound to some voltage information. The Arduino processed it to figure out, when should I output a high voltage or a low voltage to synchronize the equipment. That was sort of the workflow. So I hopefully that sort of addresses your question a little bit, Sylvia, from
Yes.
our standpoint, how this fits into the lab.
Yeah, thank you.
I had a quick question. We got a second. That's not directly connected to the lab, but kind of connected to this kind of ideas. So I'm someone who likes physics a lot. That's kind of why I'm here. But I know nothing about coding. Is there a place I should start? Do you guys have any thoughts on that?
There's a lot of websites. There's a code.org. There's a bunch of things bunch of websites that help you start. But if you were interested in kind of like learning how to use the Arduino, if you go on the website for the Arduino, there's a lot of tutorials right away on how to do it, from simple things and then all the way up to complex things. And there's like a whole community out there of just Arduino.
So depending on what type of code you're specifically looking for, there's like Arduino, which is a mix of JavaScript and their own code. But there is different types of code that you can learn. You can learn Python. I think it's CCC. It's JavaScript. There's a lot of code that you can learn depending on what you want to learn. There's a lot of places where you can learn, especially like you said, code.org. That place teaches you a lot depending on what you want to learn. But there's a broad aspect of coding. Coding is not just one language, it's a lot of languages. So depending on where you want to learn, there's a lot of places online that you could for sure learn. I took, last summer I did a coding class during the summer, and they used a website that just taught you a whole bunch of either HTML, JavaScript, Python, like whatever you would want to learn.
Yeah, but ultimately I'd recommend code.org.
Yeah, I was gonna say that, especially for beginners, like if you want to make an app or a game, like that's the best place, especially since they have lessons and they teach you like step by step. Like I actually did that. We did it in class actually, and it was really helpful. But if you want to do animations or something, there's also p5.js, and we also use that in class, and that helps you with that. And it also has a whole page of instructions and tutorials.
Thank you. That's very helpful.
Yeah, the best way to learn is to do it. I recommend just like getting your hands dirty.
Kind of want to. I know I'm not with the Hutzler lab, but I mean I did coding last year for mine, so I would say if you've had like just zero coding experience, whether it's computer science or computer programming or web programming. It doesn't really matter like what platform. I mean, you could use code.org. I don't know too many platforms, but I think just build a solid foundation, definitely develop a strong logic sense, I think, because that's from what I've seen, my experience coding at Caltech last year, it was definitely a lot of the logic that you kind of spend a lot of time working out. It's not so much, you know, syntax between languages or something like that. It's really figuring out how to get there and the steps to get there and how you're going to write that in the code is usually a lot easier after you figure that out.
Thanks.
This is great. I love this back and forth and feedback and sharing. I think, I'm probably speaking for Mitch, that is what this program is really kind of steeped in. Sure that you guys have an opportunity to learn from each other as well as the faculty and the mentors. And so from both presentations, I would hope to say that was reached. And I do want to respect the time frame that we set. I know there are a few people who need to jump off to other obligations. And so I wanted to pass it over to Mitch to do a little closing remark for us.
Sure, thank you. I just want to thank you all, mentors, teachers, faculty, of course, who opened up your labs and your space virtually to take on these projects. I know this has been a challenging summer for everybody, so I was first grateful to the faculty for agreeing to do this and for the mentors to step up and our teachers to really provide this opportunity. I'm very grateful to all the students who signed up and said, yes, I'll try this. And I was just very happy all afternoon listening to all of you talk. I'm just so impressed with what you all accomplished this summer. And just thank you all for everything you've done. I'm feeling very happy on a Friday afternoon, I'll tell you.
So I would say everybody stay in touch, especially teams information. I can say my little geniuses, I will be checking up on you guys throughout your senior year. I have your numbers and your emails. So I'll be checking in on you guys. And I hope everyone enjoys the rest of their summer.
Yeah. Bye. Thank you.
Thank you.
Thank you, everyone.
Yeah, thanks for the opportunity.
Great.
Thank you.
Bye-bye.
Bye, everyone.
Bye, everyone.
Yay! We did it. Bye, Nick.
Yes, that was I can't believe it worked as smoothly as it did. I mean,
I know, right?
right? Yeah.
Fingers and toes crossed the whole
Yeah.
time.
I think you know, I would have just been happy if they learned some stuff and didn't even finish the project, but they finished the project, so that's even better. I mean, it's especially good for them just to have like some, you know, real concrete feeling of accomplishment, like I did the thing.
Exactly. I think they
yeah.
feel well challenged and that they came. I was really impressed. We really were on there like all afternoon yesterday up into the evening and texting me back and forth pretty much all week.